So today we are going to derive the relation between Young's modulus, rigidity modulus and the Poisson's ratio. So as we have learnt in the previous derivation, the relation between the elongation strain, compression strain and the shearing strain. The similar figure we will use here to find relation between y, eta and sigma, that is Young's modulus, rigidity modulus and the Poisson's ratio. So we have to consider a surface of a cubical structure, that is A, B, C, D. The BD surface is fixed. The surface BC is fixed to a rigid support and a force F is applied tangentially to the upper surface AD. So as we know, there will be shift in the layer by layer structure, and hence finally if we consider the upper surface, A shifts to A dash and D shifts to D dash. So the angle made by the new position with the previous position from point B is theta, and angle made by point D dash, the new position with point C and the previous position D is theta. So A, B, A dash is theta and D, C, D dash is theta, and this theta is nothing but the shearing strain as explained in the previous class. As there is a small change in angle, the shearing strain itself can be considered as theta, which will be equal to the change in the dimension, that is x, and the original length of the cube, that is L. So now what we observe, that as previously only explained, that there will be elongation due to the tangential force in the diagonal BD, which is now after the elongation it is BD dash, and there is compression in the diagonal AC, and the new position it takes AC dash. To find out how much change is there when the elongation or compression takes place in the diagonal BD and AC respectively, we will put a perpendicular A dash y on AC and dx on BD. So the perpendicular suggests that now A dash C is equal to YC and BD is equal to Bx. So the diagonal BD gets elongated by the distance xd and the diagonal AC gets compressed by AY. So that is what we have written. We have fixed the BC and along AD a tangential force is applied. So A changes to A dash and D changes to D dash, the new position after applying the tangential force. So there is elongation in the diagonal BD, which is now BD dash, and contraction in the AC, which is now AC dash. So we will put the perpendicular A dash y to AC and dx to BD, which suggests that now A dash C is equal to YC and BD is equal to Bx. So this suggests that, as explained, BD gets elongated by XD dash and AC gets compressed by AC dash. Now we have to understand one more thing. If we apply the tangential force F along AD, then there is elongation in the diagonal BD, which is BD dash. So due to this is elongation means you have a kind of tensile stress. So the tensile stress leads to the elongation in BD which is now new position. With the new position it is BD dash. And there is a compressive stress along AC which also helps in the elongation of the diagonal BD. So the change XD dash, we understand it is due to the tensile stress along BD and due to compressive stress along AC. So taking that into consideration, if we say that there is a tensile stress, then there is a longitudinal extension, means longitudinal strain working along BD and the lateral strain working along AC. So we, in the previous class we have learned, if there is a longitudinal strain, then the strain it is defined by alpha, which is longitudinal strain coefficient, and beta, which is due to the lateral strain, we define it as lateral strain coefficients. So taking all these things in consideration, we will derive the relation between Young's modulus, rigidity modulus and the Poisson ratio. The contraction in AC will be A dash. So what we understand, there is a tensile strain along BD, therefore extension along BD due to tensile stress will be equal to BD T alpha, and extension along BD due to compressive stress along AC, that will be equal to BDT beta. This is along BD only. How to understand this alpha and beta value? We know that alpha is equal to longitudinal strain per unit stress. So we can write it as longitudinal strain, it will be the change in length divided by the original strain, means extension divided by original divided by stress. So stress here we are considering as T, this original length what it is BD, both stress and original length BD, that is T and to BD, will get multiplied with the alpha and you will get the extension value. So we have written as the extension along BD due to tensile stress along BD is BDT alpha. Similarly beta, we define it as lateral strain per unit stress, and lateral strain will be defined as compression along AC divided by original diagonal divided by stress. Stress is T, original is your BD, and compression what we have to find it out. So BD, this will come to the denominator as it is in the division of numerator, BD into T into beta will give you the lateral strain. So we get extension along BD due to compressive stress along AC is BDT alpha, and extension along BD due to tensile stress, that will be BDT alpha. So these two factor leads to the by XD dash. So the total value of xd dash is because of the extension due to tensile stress and extension due to compressive stress. So, we will add these two, we will get BD T alpha plus BD T beta. BD and T is common, alpha plus beta, and BD is the diagonal. BD is the diagonal for the length of which we can find out using Pythagoras theorem, as BAD is a right angle triangle. So, AB square plus AD square will be equal to BD square. So, BD square will be equal to L square plus L square, that is 2L square. So, BD will be equal to root 2L. I have explained in my previous derivation. So, what we will get here, BD is equal to root 2L T alpha plus beta. The value of xd dash is equal to root 2L into T alpha plus beta. We will number the equation 1, 2. So, next we will try to find out the value of xd dash, and we will repeat the similar process what we did in the earlier derivation of relation between compressive strain, shearing strain and the elongation strain. So, in that figure we saw that as it is a right angle triangle, the diagonal divides the right angle triangle into two parts. So, this is 45 degree, means ADB is 45 degree, and theta, as the change is very small. So, what we have to consider that ADB will be equal to AD dash B. So, this is also 45 degree. So, taking this triangle, we can write it as, so xd dash will be equal to dd dash cos of 45 degree, and dd dash we know it is a change in the position which we have written by x, and cos 45 will be equal to 1 by root 2. So, xd dash will be equal to x by root 2. So, if we substitute the value of equation 4 in equation 3, what we get, that x by root 2 is equal to root 2 into L T alpha plus beta, or x by L, this L take it to the denominator, this root 2 it will be 2 into T into alpha plus beta, x by L 2 into T alpha plus beta. So, as we know, the rigidity modulus is shearing stress by shearing strain. It can be written as T divided by x divided by L. So, this equation 5 we can rearrange as 1 by 2 alpha plus beta, take it to the denominator, and this take it to either side, will be equal to T into L divided by x. So the above equation also can be written as TL by x. So what we get, that 1 by 2 alpha plus beta, that is equal to the rigidity modulus, or if we interchange the equations right to left, left to right, we can write it as eta is equal to 1 by 2 alpha plus beta. Now further we need relation between y, eta and sigma. We need to get from this alpha beta the relation Young's modulus y and the Poisson's ratio sigma. So for that what we do, we'll divide the numerator and denominator of the equation by alpha. So 1 by alpha will be equal to 1 by 2 alpha divided by alpha is equal to 1 and beta divided by alpha. Now what we know, alpha is longitudinal strain coefficient. So what we understand, alpha is longitudinal strain coefficient, which is defined by longitudinal strain per unit stress. And we know the Young's modulus is longitudinal stress by longitudinal strain. So alpha, it will be reciprocal of Young's modulus, and also what we know, beta by alpha is Poisson ratio. Means earlier we have learned the Poisson ratio is defined as the ratio of lateral strain coefficient, which is beta, and the longitudinal strain coefficient, which is alpha. So if we substitute those two values, we get eta is equal to y divided by 2 1 plus sigma, or y is equal to 2 eta 1 plus sigma. So this equation 6 gives the relation between, this equation 6 gives the relation between Young's modulus y, rigidity modulus eta, and the Poisson ratio sigma.